Let me introduce you.
Oh, I'm sorry. He wants to.
Are you recording? Hi, I'm Tim Brown. Our presenter is for Shick. His helpers are Jeff Sonstein and Karl-Heinz Kremer. So, turn it over to you. Thank you for all your work putting this great project together and all the support you've given our participants in the handouts and all the links and projects. Hopefully they'll become great programmers after this.
Okay, after all of that.
After all that, yes.
We can skip this slide. Let's see. I wrote myself a lot of notes so I don't forget to tell you things.
Really?
So today, this morning, for the next 3 hours or so, we're gonna try to learn a little bit about how to program. I'm not gonna teach you C. I'm not gonna teach you the Arduino functions. Those are, if you've done the projects, you've got a peek at both of those, the functions and C. But we'll get started with some programming. And like I said, you've already got a head start by doing some of the projects. Now, let's see. How does this work? So one of the ground rules is, don't let the slide go by and ask the question 5 slides later. Because it's too late. And I have about 85 slides here, and I want to do them in an hour and a half. Because I want to get to programming. I don't want to, you guys came to the program, and after somebody presented a similar academy a few years ago, the people were upset because all the presenter did was talk and never got to programming. So I intend to get to programming. That's also why we're going to be here till 2:30. So there's no way we can cover this stuff in an hour and a half into program. So for the next hour and a half, if somebody will stop me at noon, if we aren't done with the slides by noon, tough, we're going to move on to programming.
I'll set an alarm.
Okay. So
Alexa, stop Forrest at noon.
So for those of you who weren't at the club meeting the other night, I've been programming since about 1980, I think. So my first 2 projects were these 2 devices on the left. One was a handheld terminal, and then a battery-operated printer. And my last 2 projects were this remote light control that was actually an RF link between the wand and the light, and so it's meant for like the top of a utility truck. So when the guy climbs the utility pole at night, he can control the light to point at what he wants it to point at while he's up on the pole. He doesn't have to keep running down the pole. The fun one was the last one on the right. That's a beer tap. It'll pour a 16-ounce glass of beer in 3 seconds. It can pour beer faster than the bartenders can make change. So, anyways, that was a fun project. Had lots of water all over my garage and all over my basement in the winter, perfecting the software. Okay, primary resources, the Arduino website, and I like these 2 other websites for looking up stuff on C. The C programming website, Tutorial Point. On the other hand, there's a great book that you don't want to read. It's by Koenig
and 12.
Koenig and Ritchie. K&R. It's the Bible for how all the C functions work. And I made the mistake of trying to read it once, and you don't read it. You look something up in it, but you don't read it. So that's a really cool book, and if it still exists, there's an answer book that goes with it that answers the questions in the book. So when you can't figure out what they just tried to tell you, you try to answer their questions. There's a book that tells you the answers to that. But anyways, that's those are good resources. And then there's lots of resources out there. That first one, download the free book. I didn't read it, but I did download it, look through it. It looks like it's a pretty good, hey, if you want to get started, look at me type thing. And Tim Barrett has a book from the ARRL that there are some books with programs and projects in it if you want to get started. Okay, so the first big thing is, what is programming? And we've got, and some of you, I guess, are programmers already. So my version of what I'm programming is what we're going to talk about, because I didn't go to school to learn how to program. I learned how to program on that data terminal. That was actually a military data terminal for a small company that made radios for third world armies. So mine is input, process, and output. Input, well, I guess you gotta go the other way around. Take the output. What do I want out of this program? And the input, what am I gonna put into this program to get the output? And then the process. What are the steps I have to go through to get there? And I'm sure Jeff and Carl can give you their own versions of what programming is. But this was mine. And so my question to you is, how do you write a program to tie a shoe? So what would be the output? This is the class participation part. What would be the output from a process that's how do you tie a shoe?
Tie shoe.
All right, very good. What would be the input?
Shoelaces. I don't think it has an input.
Okay.
An
Well, it does.
handle that
It's your shoe.
trips when you.
An untied shoe.
Well, that's putting a qualification on it. Yes, could be. So you've got this black box, and out of the black box is gonna come a tied shoe. And so you're gonna put a shoe into the black box to get it tied. What are the requirements on the input? You know, it's just not, I'm gonna put a shoe in there.
Shoe with laces.
Yeah, it's gotta be a shoe with laces. You aren't gonna put a loafer in there. Are you gonna put a shoe by itself, or is it gonna be on your foot? You know, it's probably gonna be on your foot. What good is a tight shoe if it's not on your foot already? You know, so there's some things to look at the input. And then the process inside, yes, there's all the mechanical stuff of grabbing the string and tying the shoe, but you also have to say, are the shoelaces too short? Can I tie it? Are they too long that I have to cut them off when I'm done tying it? Is the shoe already tied? Anyways, that's just a real, I guess, simple output, input, and the process. That make sense? Bring up questions? So no matter what you're going to do, you have to go through that in some fashion, like the rotator controller I proposed at the end. You have to figure out what it is you want it to do, what information do you have to do it, and then how do you actually get the rotator to turn. So, okay, we'll stop for a second here, and have all of you done some of the projects, or anybody done all the projects?
All right.
All right, two. Anybody done none of the projects? Okay,
That's good.
well, you only had a couple of days, so you're forgiven.
As far as trying to compile it,
Yeah,
that's where I wrote.
okay, so I guess for the most part, I was gonna, if there was a group that had done it and were gonna be bored with the next part, I was gonna divide it up into two processes, but I'll continue through. So one of the projects we're gonna do when we get that far is programming a 24-hour clock. How do you make a 24-hour clock? I wasn't gonna do that until I was trying to record time on a contact, and I realized, none of my clocks show UTC. So I have to have a 24-hour clock. So the slide was written as if I was going to divide the groups in half. I'm not going to divide you into two groups. So we'll just continue through so you can ask questions. Well, we can do this part. If I'm going to make a 24-hour clock, what do you think are my processes, my input, output, and how do I do it? Any
No, you need
Any
the date,
requirements pre-thought?
you need the date and the start time, or the current time.
Okay, so you need a way to get that in there.
You need to drive the display
You drive
for
this
the
way.
Material list to start out with?
Well,
Specs?
Yes, but we're doing software. The hardware guy took care of the material list. But you've got a clock, something to create a tick. You gotta have a clock for that. So, and then you gotta take that tick, and you gotta turn it into seconds, and then you have to display it. And you have to handle seconds, minutes, hours, day, month, year, leap year, different length months. So there's a lot to think about.
You need a mechanism to set the clock.
Yep. We're not gonna do that. That's a little more complicated than, excuse me, a little more complicated than I was planning on. Okay, so the programming language is, my understanding of the Arduino IDE is, I'm sorry?
Sort of C.
Yeah, they wrote functions in C, and they kind of support C++. Is that fair?
A little bit object stuff, yeah.
Yeah.
Actually, if you want to get into library programming, it is C++,
Okay,
but that's not today's.
right, that's way over. If I get that far, I'll mention it, but go ahead.
Just real basically, what's the difference between C and C++?
Maxwell, want to handle that?
C++ is basically C with an object-oriented set of syntactic sugar over the top of it for the programmer.
Got it.
Compiler, most compilers actually do the same stuff, everything in C and all, yeah.
Thanks.
So there's some more resources. Excuse me. So this is the Arduino some of the references in the Arduino website. So if you go on the Arduino website,
Tell them what function it is,
good point.
like the ones up there on the board.
Okay, so
You asked for it.
I know I did. These are they all? Yeah, these are all functions. These are actually like subroutines. Yes,
Want
sir.
me to give that a stamp?
I'm sorry.
You want me to give that a stamp, a function?
Sure, go ahead.
So I'd say a function is a way to collect a group of programming lines that you want to reuse over and over again, and add some ability to change some parameters. Like if you want a delay, you might have an input time, so you could write a delay that'll pause for a certain amount of time, let the person pass in what that delayed amount might be, so you can use it over and over again. It's all about reusing code. You don't want to continue to write code. You want to reuse portions. So if you have a really complex function, you want to be able to pass in a few parameters to change its behavior, but you'd like to call it all over the program whenever you do things to save time.
Fair enough. And
And the function returns a value. You may or may not use it, but
it may or may not return a value also. It doesn't necessarily have to
Yeah.
return a value. In this particular case, what they've done,
can.
right, what they've done in this particular case, like the digital read, digital write, pin mode, analog read, things like that, they're hiding the processor from you. So digital read, digital write addresses one pin at a time. And so what the command in the processor might be port D equals something, and port D is 8 bits wide. These inputs and outputs are only 1 bit wide, so they've made it easy for you. The person who's learning how to write C and how to use the Arduino, these functions simplify everything, and simplify the commands that they're trying to create. What they don't address is some of the more complex things like timers. I don't know how they would write a meaningful function for a timer, because the timers are way too complex. It's just not an input and an output. Timers have lots of different capabilities. So these are Arduino functions.
What is MKR family? Is that Zero due and NKR families, the third group down.
Oh, that's a type of Arduino.
Ah, okay.
They have different processors and different boards.
Okay.
And I think, well, I'm not gonna say anything, because I haven't looked at the MKR family. I just know there are boards that are MKR something or other. See if this will let me do that. But just for the sake of looking at it, here's the random function. Excuse me. And so you see, they tell you about it. You can just random a group of numbers between some 0 and some maximum. So you can pass it, like I wanted a random number between 0 and 10. So I could just pass it at 10. I can pass it a min and max, so if I want a random number between 100 and 200, I can say random 100, 200, and it'll pass you back a random number. They're pseudo, they're not true random numbers, although if you start, it gets a little more involved. You can make it look more random than they have, if you just don't call this. They have a random seed which you can plug in, and then if you randomize the random seed, it begins to look more and more random.
Would it generate this number every scan? Would it regenerate a random number every scan?
Yeah, every time you say randomize, it'll return. In this case, it's actually returning a number. It'll return a random number, and it won't be the same number, obviously, it's random. So like on that, if you saw the Morse code thing I wrote an article about, the random code generator uses this. And depending upon whether you're just doing the 26 letters or the 10 numbers or every single Morse code character, the min was always 0, but the max was like 26 to get 26 letters. Okay. Now how do we get back to what I wanted to get? There we go. Oops. So, a quick look at the IDE. We probably should look at that live. When you start your program, you get this, and they have a nice tool here. This is the only thing I don't like, and other true programmers, I guess, like it. I always move it down to the next line, and you probably saw that in my notes, because to me it frames what you're writing. I have a hard time finding the ones hidden up there. So when I write a simple program, you can see I've moved it down to here. And so my view of what they've written, you see when you write an Arduino program, if we go back to the old slide, you see there's a setup and a loop, routine. Well, in C, you write a main, and so they've hidden the main from you, and they give you a setup, so it's really obvious where you put your initialization. And then the loop is where you put your program. And so at a C level, not an Arduino IDE level, your program may look more like that. Void main, and then a setup function and a loop function. And a loop function just goes around and around and around and around and around indefinitely until you do something to stop it. Question before I...
Is that a strict rule of C then, that it always has a loop?
Yeah, C is not, not
Right.
it's not an operating system.
Yeah.
You could write an operating system in C, but yeah, C just runs around in circles, especially on a microcontroller.
Okay.
I think he was asking if you needed a loop in every C program, and only on, not in regular C for a big.
Oh, right, okay, this is a C.
This is an Arduino
got
specific
it,
case.
okay.
Oh,
Right.
thank you, Jeff.
Yes.
Yeah, it's what you have is a main
Yeah.
in a C program.
If I may add something, so for example, on a PC, if you have a program written in the Microsoft Foundation class, you would have individual functions that are then called at various times by the operating system. There's not one loop, because your program switches in and out of context.
Actually, the operating system is the loop.
Yeah.
Yeah. So, thanks. So if you've gone through this part way, we won't look at this, but these were the instructions. Most of these slides are directly from the documents I've sent out. That's why I think we can go through 85 slides in an hour and a half, because you've already seen and read them. Excuse me. So if you have a question as I'm going through these, please stop me and I'll do my best to answer them. So this was, you downloaded the zip file and just told you how to open it. And what I was trying to get you to do by doing it this way, as opposed to installing the IDE on your laptop, is to keep whatever we were doing in this class separate from whatever you've done by yourself. And that's where creating the folder called Portable. Somehow if you create your own IDE and then put Portable in there, it magically keeps everything there, and it's not using all your other files, I guess. So like I only have one. I've been running mine for this class. I've been running mine off the memory stick so that they don't get contaminated. So there, how do you start? You click on the EXE. The Nano, or any of the Arduino controllers, you just plug them into the USB port, they power up and they're running. So if you don't need any hardware, it runs by itself. So there's the blinky program. The LED will blink. You don't need any hardware put around it. All the Arduinos have, I believe at least the Uno, the Mega, and the Nano all have it on D13. You have to remember to set things up. I've learned from people's emails that there's actually newer Nanos that don't use the old bootloader, that use the new bootloader. So that was an interesting thing, why they changed midstream. Setting up your COM ports, that, especially when you've got three or four going at once, each one comes up as a different COM port, and it really gets confusing. Which one is that COM, 3, 5, or 11? You know. So here was my goal, was to get to a point where we could talk about making a digital interface to this old rotor controller. And Tim pointed out this morning that it's in the book. I've already done it, but it's in the book, and I didn't look at the book. So it'll be interesting to compare what I've done. The other thing is the station clock that we talked about, and if somebody is really brave, I put together 4 switches and 4 LEDs in case somebody wants to try writing a Simon program. Do you remember Simon? It was the round game with the 4 colored lights, and you press it would flash, and so you press the button, then it would flash 2, and you have to press them in the right sequence, and you have to remember. Writing the program for that could be quite interesting. Notes are, adding comments is extremely, extremely, extremely important, especially once you get past like 3 or 4 lines. Why did I do that? You know, come October, why did I do that? They're a pain in the neck to put in the program, but hey, guess what? In October, they'll be worth all the time it took you to put them in the program.
Can I interrupt something?
Yes, always.
Some people actually write a lot of their programs by writing the comments first. So you end up with a page of headers for all the functions you're going to write that explain what they do first.
Interesting.
Different styles for different folks.
Right. So find a method in all of this, all of the things that I'm talking about are really, we're talking about it from my point of view, how I do things. So if you find a way that works, be consistent. And that's a cool way. What Jeff just said, you can plan out your program ahead of time and then write it. That terminal being my first attempt at program. Back in the old days, they used to have tablets of paper with all the circle, squares, and diamonds for writing flowcharts on, and I had pages and pages and pages of flowcharts for this thing. And because we didn't have nice computers, you know, we had the Silent 700 hooked up to somebody's homebrew 8-bit computer, and we were trying to compile on that, so you didn't want to spend a lot of time writing comments and all that stuff. But that was quite a long time ago. As you saw on the slides for each of the programs, I tried to give you links back to the Arduino website for what the different things, what the left bracket means, what the equal sign means, and all that. So you could, if you didn't know, you had a resource readily available. The Arduino IDE has no real way of debugging except flashing the LED and the serial monitor and serial plotter. So if you were actually doing this with a development system, you could set a breakpoint, and so it could run to a command and stop, and you could go in and look at what are my variables, and you weren't going to do that with this unless you stopped and used the serial monitor to print out everything. Adding the serial commands uses up a lot of memory, number one, and it slows everything down that you have to do. It stops and waits, so it sends out the serial character, and then it moves on to the next instruction. So just a quick look. We did this already, but on the Arduino website. But here's pin mode. When you go to the pin mode, you get a description, syntax of how to use it, what the parameters are. So like in this case, the mode is input, output, or input, pull up, and a pin mode doesn't return anything. But a digital read will return the status of that one pin, a 0 or a 1.
Notice the capital letter.
Yes. Go for it.
These are what are known as constants. They're, from the perspective of an Arduino programmer, they are basically just magic thingies out there that you can call that are pre-configured with what you need. So you don't need to actually know what is any of things inside that mode. You just need to use one of those. You don't need to know what it is. It gets really messy when you use the numbers that are under the hood, and then you go back 6 months later and you can't tell what you do. So if you see something all caps, it's a constant. If you're going to write a constant, convention is use all caps so you can tell later on it's a constant.
And whatever you do, do it the same all the time. And I think that one document I sent out, which was the requirements for the software requirements for a STM32, some kind of microcontroller. I stumbled on that when I was working on my IQ32 radio, and I wanted to share it because it does talk about all these things. How to write, how to define it, how to write a variable, whether it's all lowercase or camel case, which is like pin mode. It's got a capital M in the middle of it. But the important thing to take out of it is just be consistent. So this is the C code behind, and it's not even, well, this is the C code behind the pin mode instruction. This is what the Arduino people wrote to hide all the registers from you that pin mode has to deal with. Because it has to decide which of the 20 plus pins you're going to make an input or an output, which pin gets the pull-up resistor, and all that. So you don't have to know this yet. You'll get to there when you decide those instructions aren't good enough and you need more control over what you're writing. But just to show you the work they put into creating the IDE for you, they did do a lot of thinking, because this isn't just for the Nano. This does the Uno, this does the Mega, and the Mega and the Uno are two different processors, so things are slightly different. And I suppose it does more than just that, but the point is, somebody did a lot of work to figure these things out so it works seamlessly for you when you're trying to learn to write. So getting started, like I said, here's, excuse me, I gave you links to the different things you were going to use in the programs. Told you how to save the programs. You can see I moved the opening bracket down to the next line. Some of the commands that were used in writing the program. And what you saw in there somewhere is like LED built in is equal to 13. And 13 means D13. And D13 is not a pin on the, is not the definition of the pin of the microprocessor. It's Arduino's definition of the pin of the microprocessor. So you will see D13 on your Nano board, but I didn't look it up, but it's some other port pin that is not, most likely not a D, if you were to look into the microprocessor's data sheet. So that was the purpose of this sheet. It gives you a cross-reference between the pin numbers on the board, Arduino's pin numbers. Let's see if I can find these. You see D13 out there somewhere. I think it is PB5. Yeah, there it is, D13. It's the bottom right on the board drawing. And so it's port B bit 5. And yet they call it D13, and they program it as 13. So again, that's why the secret decoder sheet. Took me a day trying to figure out what were they trying to tell me, because I'm looking at the microprocessor data sheet, I'm looking at their code, and I'm saying it doesn't make sense to me. It took me a while to find that.
Now, to make this a little bit easier, the D13 is actually printed on the circuit board.
Yes.
So you just need reading glasses so that you can decide whether reading is going.
And a bright light.
So you must compile this against a header, a prototype that's for this particular processor, and the Uno would be a different header file that would
Correct.
put that,
And you said,
yeah.
see up there where it says board, and the picture of board, Arduino Nano.
Yeah, oh yeah.
If you go to that, if you were to put your cursor on that, there's a whole list of all their boards, and you have to pick the right one. And be careful picking the Nano. I think there's more versions of the Nano than you can shake a stick at.
He went.
So here's our simple program. There's a simple loop. It turns it on, it delays, it turns it off. The LED off, it delays, it goes back, it does it again. Important thing to know about delay is you can't do anything else while it's delaying. If you say delay 1 second, you are stuck at that point in the code for 1 second. It's not, I don't know what delay does, but it's probably counting down from something to 0. And so you can set delay in 1 millisecond steps. And it's not perfectly accurate. It's not perfectly accurate. One of the simple reasons is the 16 megahertz clock isn't 16.00000. It's whatever happens to be on your board, plus or minus a few tens or hundreds of hertz. So if you're thinking you're going to make a clock that's going to keep time accurately for a year, it won't.
Is there an upper or lower limit to the delay in milliseconds?
I don't know what the upper is, but the lower is obviously 1. And the
It may
instruction.
not do 1.
I'm sorry, what?
It may not do 1, even if you tell it
Oh, okay.
delay for 1/1000th of a second. It may always do at least 10,000ths of a second or something like that.
Oh, okay.
Let me look this up.
It's really hard to predict the granularity.
But it works as a delay. If you're not trying to do something really accurate, don't try to measure frequency with it. That's what the timers are for. Okay, we'll continue on while Carl's looking it up. To compile, you just click the button, the arrow button. The check button just does a compile without a download. So if you're writing code and you want to see, am I doing okay, have I got any bugs, you can just click that. And you don't have to wait for the download to occur. To move on, you can do a quick compile, the errors will show up, and I never put an error screen up there, that was something I missed. The blue bar at the bottom tells you how things are going along. The black bar gives you the results, and that's where the error messages will come up. When you get an error message, scroll all the way back to the beginning of the list, because that's the error. All the rest of them are the errors that are caused by that first error. So if you go back, you find the source of the error. And it's not necessarily obvious what the source of the error is, because the error occurred on this line, and the error might really be on the line before. But that's, even in a compiler, I've seen that happen, where it gives you an error on a line, but it's really what you did in the statement before, and the statement before could be a subroutine before. So, anyways, just something to think about if you get an error and you can't figure out what's going on. Go back a line.
Or if you remind me like the little square, sometimes a little square comes up around,
Thank you. That's a good one. Do I have, let's get rid of that. He's talking about this little square right here. That, you see the cursor's down next to this one, and that just tells you where the beginning of the function is, or beginning of the bracket. If your function actually goes off the page, it'll tell you up at the top, so when you put your cursor down here, it'll tell you up at the top the name of the instruction that it occurred in. So you can scroll back to it. So I thought that was pretty cool.
Yeah, I found that really useful.
Yeah.
Table right down.
Going through all my old programs, thinking about all my old programming, trying to figure out where does that link to. I print them out and I draw lines. That goes there, that goes there, that goes there. And, you'd have 5, 6 sheets of paper taped together, trying to figure out, this goes all the way back up there. We'll skip these. Blinky 2, just more things that you're going to use. So here's where you stick in the serial begin. You have to do that because you have to tell it how fast, what the baud rate's going to be, and that also does whatever initialization is required. Print line prints what you tell it to print on one line, does a carriage return, and takes you to the next one. And there's a print statement, which you saw later, which just prints and stops. So you can print, because there's no way to print 3 things from one statement, at least not that I found. Carl, did you ever?
It looks like the delay is pretty accurate, plus minus a few microseconds. There's a delay microseconds, which starts to get fairly accurate above 3 microseconds.
Oh,
So you cannot do 1 or 2. It will do something, a short delay, but you don't know exactly how long it is. So the delay should be fairly accurate.
fairly accurate based on how accurate 16 megahertz
Right.
clock is.
Yeah.
Cool, I didn't know that, thank you. So if you compiled and run it, it went let off, let on, let off, let on. You had to be sure and set the baud rate on your, on this also, so that the board could talk to it. Okay, the next thing we did was add a push button. No big deal. You probably, if you're a hardware designer, you say, where are the pull-up resistors? The pull-up resistors are inside the processor, and that was the input pull-up instruction. Turn that pull-up resistor on, so that you could have a 1. Otherwise, you had a 0, or maybe a 1, and maybe a 0, depending on how it's floating. So that's why you need a pull-up resistor. There's all the commands and references to them for this. And so this made 8 or 4 different versions of this just to show you how to use different instructions and different processes to get to the same result. So this reads button 1. If it's closed, it turns on the LED. If it's not closed, it reads the other button. Oh, wait a minute. This is just one button at a time. So if it's closed, it turns on the LED. If it's open, it turns off the LED. And so it executes all of those instructions over and over again. Even though it's already on, it's going to try to turn the LED on again. Even though it's already off, it's going to try to turn the LED off again because it's not looking to see, are you on, let's skip it. This one, I just combined it into one instruction. It's either on or off. So it's made the loop shorter. What was the difference? Okay, so I moved the reading into the if statement. And then I just did it all in one statement. So if you're not familiar, it reads the push button, and because I was making the button being closed, which is a 0, turning on the LED, and to turn on the LED it has to be a 1. So that's what the exclamation point is, the not of reading the button. So when the button's 0, what goes into the digital write statement for the LED is a 1, turn the LED on. And vice versa, when the button's a 1, the 0 goes into that statement. And so there's the 4 routines side by side. Just, here's what they look like. And the question might be, why would you have all these different things? I think you might use something like this. You just want to flash a LED. So every once in a while you call the routine and it does nothing more than change the state of the LED. So if you just want a blinking LED on your front panel for some reason, that's what that might be for. And others, well, I guess you'd have to be writing a program. I can't think of something off the top of my head to give you an example. This one is probably just a little out of control, meaning
Unless you
it's
want
too
to,
wordy.
unless you want to do multiple things based on the
Okay.
status of the LED.
Okay,
That's
good.
where that becomes useful.
Thank you.
But it may also be the way you develop the program.
Yes.
When you first start out, you may not know what the best way is to do a certain thing. And you may end up with something that uses 50 different commands. And then while you're doing that, all of a sudden things start to crystallize. And then you realize, yep, I can do this more elegantly. I can do this quicker. I can compress this into a function. And then you end up with something that is more concise and at the end easier to understand than 50 lines of code.
Beware premature optimization. Don't try to optimize when you're writing the initial code. Do like you said, get it to work, and then you'll see optimization.
Yeah, thank you. Both good thoughts. 2-button, check one button, check the other button, and I made them do something. So the first one makes a dot, the second one makes a dash. So you've got a little keyer all by yourself with 2 buttons. Oh, that's the same thing. So here's what Carl and Jeff were just talking about. I've got these two sets of instructions, digital write, delay, and come down here, same thing, digital write, delay. They're very similar. The only difference being this first delay, how long is the LED on for? It's on 120 milliseconds there and 360 milliseconds there. So now I can say, I can optimize a little by, I can call a subroutine and pass it that duration. So I created a subroutine with this one set of instructions, and instead of 120 or 360 being in there, I called it time. And so I pass the value of time to the data and it sticks it in there, and it works. So now I've eliminated 4 lines of instructions. And you can pass more than one value into it, into the routine. You can only get one value out if you're making it equal to something. And this is kind of a place to talk about the scope. This variable time only works inside this routine. It doesn't work up here. This part of this routine, the loop routine, has no idea what time means. Because I defined it inside this routine, that's the only place that that knows what time is. If I had put int time up here, then everything, the whole program, would know what time was. Good enough start on scope? Okay. Okay. So here's here's a comparison of the two button things. So this one looks more complex, this one looks simple, because it's got this little subroutine. So where here, if there was a bug, you'd have 2 places to look for a bug, or more, depending on how many buttons you've got. Here, I've only got 1 place to look for the bug, so I've simplified not only the code, but I've simplified my debugging, I've simplified my comment writing. Okay, so now we're going to add a speaker, and using the second case, I just stick the speaker command right in there, and this is one of their functions, tone on, or tone, and it actually, the tone has 1 or 2 parameters you can send it. You can send it tone on with the frequency, and then you're going to have to tell it, there's another command that says no tone. Oh, that's got, let me read this again. It can have 2 parameters. One is which pin you want the tone to come out of, got to get it right. Which pin you want the tone to come out of, and then the frequency of the tone. Excuse me. But that requires that when you want to turn the tone off, you have to send a no tone command. You have a second version that has 3 parameters, which just adds time. So you can tell it how long you want the tone on. So you don't have to send a no tone command to it. You just say which pin, what frequency, and how long. So that's where the 120 milliseconds came from. In using the tone, you just pass it the time. It's right down here. See, so the pin was A0. The analog pins, you use an A in front of the pin number. The digital pins, you don't use anything. Another thing to remember when you're trying to write code for this. Loop instruction. Okay, so the loop, the loop routine goes round and round, but sometimes you need to do things. I need to go iterate through a process 10 times, so I have to write a loop inside my loop that goes for 10 steps. And so that's what the for loop does. So in this case, I use 2 of them, so you can see 2 features. The first one here, I start with I equals 0, and I go to, I will increment I plus plus over here, and it'll run this loop as long as I is less than j. And so up here at the beginning, I created a variable. I said j is equal to 1 when I created a variable. And so I go through, the first time I go through this loop, it's going to do it once. This will become 1. So I start out with I equals 0. I do this with a serial print, the delay, I come back up here, and it increments it to 1. Well, this 1 is not less than this 1 because I defined it up here as 1. And so I go down and do this one. And you can see in this for loop, I've left out the beginning I because I'm using the I from the previous. So whatever the I was here gets put in that place because I've already used it. And so it does.
Need decrement.
Well,
And this pause,
Yeah.
Forrest,
Oh, I'm sorry.
this pause here, when you're trying to figure out what it does,
Right.
is the reason why this is not a good idea to do.
Well, this is why it's not a good idea to leave comments off.
No,
Now,
more than that. First time through, it's not a good idea to default to the I above. Be really explicit, beat it to death, because you're going to
Okay.
get what you're doing the first time through. Serious.
Yep.
Sorry. but
No, I agree with you,
I bled from the eyes too many times.
especially correcting papers. But
But we've all
they're
done that.
right.
We've all done that, and
Yeah.
then, when you try to debug your program, you just beat your head against the keyboard because you cannot figure out what's going on, because you're missing one small detail that was obvious to you when you wrote the code, or you thought it was obvious to you, and then, it turns out, no, it wasn't that obvious, and it was actually wrong, and you cannot find it.
Yeah, they're right. It should have been more, for today's purpose, it should have been more explicit. But what I was thinking when I wrote it was to show how to use the previous parameter in this fourth statement. But you can see the problem of not writing comments. I can't remember why I did it the way I did it.
May I throw in a recommendation here?
You may.
Use a different set of letters in each for loop within a given
Okay.
function. You will find that it is much harder to rule out that way.
Could you say that again, please?
Use a different set of letters for the variables for each for loop.
Like IJK and
So
L.
IJK and then maybe ABC and then, that way you have a much harder time getting confused what's getting incremented, what's getting checked against. Whatever can be confusing will, it's a corollary to Murphy's Law.
Yep. Okay. Thank you. I appreciate you guys' input.
Or a pain in the ass, but.
I get my revenge.
Excuse me, Jeff, do you know if you can do the, like, double characters, or is it only a maximum of 26 variables?
You can name it Fred.
Okay,
For Fred equals 0 to Fred less than Mary.
gotcha.
You've got
So
constant-
there's not really a limit then to the number of variables that you can have,
Yeah.
No, they just gotta be
Yeah.
different.
just unique.
It's just convention to use singles for iterators and such.
So it all
And-
sort of depends if we understood what your intended waveform was. If you were trying to really produce this little chirp,
Yeah,
that's not a half bad way to do it, because you have decreasing and increasing values of I.
right.
Your clarity of code wants different variables, but if that's the function you want,
Exactly.
and that's the part here, it doesn't say what the intent is.
Yeah.
What do you need now, at this stage? Because Karl Heinz is correct, if you're only writing a given function in your program, if you're only going over it once and never rewriting it, that's a danger point. And you're gonna go back and rewrite it, to look at it.
I think another answer to Don's question is, the 0 doesn't have to be 0, that could be a variable also. So all these, variable equals variable, variable less than variable, and variable increment, or variable decrement, so just depending on what you're doing. Okay, so the next thing was reading the A to D, and here's where we use the serial print statement to get two different variables printed out on the same line on the serial monitor, because the print statement doesn't put a carried return line feed in there. Okay, so here you see the int AD value, and I put it up, well, there's no other routine, so it's really not that useful, but the scope of that variable would be open to any routine I put on in that file below it. So if I had a subroutine down here, it would know it AD value was. And if I had a subroutine below that, it would know what AD value was. Keep trying to turn it with the mouse. So we got a 10-bit A to D, which means you got 0 to 1023, and those are totally worthless numbers when you're trying to measure voltage. So you have to scale it. So because we're doing things in integers, if you divide 5 by 1023, you're going to get a 0. You're not going to get a .00 something, you're going to get a 0. So you've got to scale the number up, your 1023, so you multiply it by, in this case, 500,000, and you divide it by 1023, and you'll get a number that, a kind of meaningful number. So if you ran the program, you got some numbers between 0 and 499, and what you had is an implied decimal point after the first character. So 499 was really 4.99 volts. And that's, if it's just for you, it's okay. But if you're trying to do something meaningful to help somebody else, that's having to know where the decimal point goes in a number is not very useful. So that's where you go to floating points. So now you can divide, instead of by 500,000 divided by 1023, you divide just 5. You got to make sure you put that decimal point in there, because if you put 5 divided by 1023, it doesn't care that you said float. It's going to treat it as an integer division. And so you get 0 again. So now you'll get a number that's scaled, 4.62 volts, not 462. So when it prints out, when you put it to your display, it's now a meaningful number that you can look at. So whether it's voltage in this case, or temperature, or some other variable, you can scale the numbers.
Can you just say float, or do you have to include that in your compilation? In other words, is there a header file that you have to bring in, or is it always in there?
In this case, it's always in there. It's part of the IDE. They defined it. If you were writing, I think if you were writing just a straight C program, it probably would.
It's there too, it's a basic data.
Yeah.
In Microsoft, it brings in double. If you want to use float, I think you have to bring in something. Well, that's a long time ago. Probably do different things now than they did back in the horse and buggy days.
So floats and doubles are independent data types in Arduino IDE.
Yeah, are they? I'm sorry.
I believe so.
And they're different length
Yeah.
numbers. Double is
Well,
4 bytes.
floats are 32 and doubles are
64?
also 4 bytes. That's interesting.
Huh.
Anyway, I'm just looking it up in the help in the IDE.
Okay.
They're both.
Okay,
They're
so
both.
what I was, this slide you guys didn't see. I made that because I wanted to show a point. So I can make a variable and call it a constant. So now the program's not allowed to change that. So scale is a constant, and it's equal to 5 divided by 1023. And if you try,
I'm sorry, if I can read a quote real quick. The double implementation on the Arduino is currently exactly the same as the float with no gain at the same. So there you go, you can call either one. But if you're importing code from something else, pay attention. Right.
so we can create a variable called scale, and if you try to change scale down in the program somewhere, you would get, I'm hoping you'd get an error message. I didn't try that. The other thing you can do is you can come over here and you can define scale as being this number. And so now it's also constant, but now you can't change it in the program, and it won't take up any memory space. I believe this one will actually take up RAM. Oops. I believe doing the constant float would actually take up RAM. I could be wrong, but.
It depends on how the compiler will optimize this. It may just say, yep, this is always a constant, the compiler will write that into the code without picking up
Yeah,
any.
compiler might be smart. So anyways, this was just 2 more ways of creating that.
One thing that they note in the Arduino manual is that floating point math is also much slower than integer math.
Yep,
I don't think it has its own process, its own process.
no, yeah, it's instruction.
Programmers often go to some lengths to convert floating point calculations to integer math to increase speed.
Okay, the next thing we did was add a library so we can, I think, run the LCD. Now, if you looked at the libraries available in the Arduino IDE, they had an LCD library, but it was, I believe, a parallel interface. And so it took 10 wires, which means it used up 10 of your port bits, where this uses 2. This uses the I2C interface. And so you have to download it. It's not part of the Arduino IDE. So these instructions just showed you how to load it, how to include it. And how many people got this far? Or I should say, how many people didn't get this far? Oh, okay. So the first program was just simple. This is what I do. I don't try to write a program. I just, what Carl Heinz was saying earlier, let's see if it works. So I installed the library and I wrote to the display and it's like, phew, now I know I can go farther. I got that far, so I can then go on to the next program. Probably should go back here for a second. Just so you know what's going on here, this command here, so I don't have to write liquid crystal underscore I2C. I've defined it as LCD. This is the address. An I2C interface is a serial interface. And what serial means is the bits are coming out 1 bit at a time, kind of like your RS-232. You remember those. The data is being sent 1 bit at a time, 8 bits, 8-bit blocks. And so
You said this is a different library than the liquid crystal that's included?
Yes, this is a different library. That's why we had to install it.
Okay.
So you can put a lot of devices on an I2C interface. So you put a temperature sensor and humidity sensor and a speed sensor and who knows what else. And they all have, because you're only on 2 wires, each of them needs its own address. So that's what the 0x27 is, hexadecimal 27. Every device should have its own address, and the address is usually defined by the manufacturer of the device. It's not something you can assign it. There's no way to go into the display and say you're going to be 3 fox or 7 dog or whatever. It's a 27. Except in some cases, some of these interface chips, the address is actually 3 fox, not 27. I stumbled on that one time. Bill Hopkins was having trouble getting his display to work. And turns out his display, although it came from the same company as mine, had an address of 3 fox.
Do any devices have duplicate addresses?
Yep,
Different
there's only
manufacturers?
256 addresses. There's lots of devices out there in the world. So yes, it's very possible. The next thing you're passing them is how many characters in a line. So the display I've got here's got 20 characters in a line. Although I can tell it's 16 and it doesn't care. But that's not, you don't know that. So this says 16 characters in a line and that there's 2 lines. The thing to remember is the first character is character 0. The first line is line 0. So when you're writing to it down here, you see here I'm writing to character 3 in line 0. Let's put the V in the third character, in the fourth character position. Because 0 is the first character. And line 0 means line 1 on the display. And then down here I'm putting the R for Arduino program in the first character position, which is 0, in the second line, which is line 1. Once you get used to thinking in hexadecimal and binary, it gets a little easier. Okay. So then we complicated things. Just tried to show you using more than one thing in a program. So I'm reading the pod, I'm reading the push buttons. So you can see here all the initialization. Here's void setup. All the initialization is done up here. That gets executed once and it's done. Never gets executed again. Excuse me. So down here, I read button 1. I read button 2. I took the long way. I read the A to D. And then I go back, start again. And I just gave you some things to try to see what happens. Okay, so now I'm going to add the rotary encoder library. It's the same process. Debouncing. The push buttons and the rotary encoder, you need to debounce switch software. And it's not hard, just time consuming to write the code testing it. Or you can put a big cap on there and hope that between the cap and the pull-up resistor, you've got a nice RC time constant that filters out switch bounces. And switches do bounce. When I pushed the button down, it did not close just once. And when I let it up, it did not open just once. You get at least one bounce,
As far
almost
as I
always.
can tell, so I built this without the capacitors.
Yeah.
And then I put the capacitors on later. And I can't tell any difference.
Really?
It seemed to be bouncing. But
Oh, yes, I know why.
why is that?
Because what I showed you, the software I gave you,
I had debounce in it.
no, it's polling the pins.
Very
And time,
slowly.
and so the bounce takes place during the time the
Right.
processor's reading all these things. The reason I put them on there is the other version, the other method of calling a rotary encoder, and it's in the library. Well, it's in the example, I should say, it's in the example projects for that library, is you do it with an interrupt. And so the interrupts happen real quick. And so what happens is you go in and out of the interrupt 2 or 3 times each time you click it. So all of a sudden, things are, you're saying, what the heck is going on? And that's what it is. So you throw a capacitor on there, and most of the time it takes care of it. You don't have to do it in software. If you're running out of space on your circuit board, you do it in software. So here's the rotary encoder, and actually the program I've got running. Oh, you can't hear, it's too low. Anyways, so I combine the tone generation and changing the tone frequency and pushing the buttons. Actually, the push button only worked on the rotary encoder when it said open and close. They didn't address the other 2 push buttons. So I've got you a chance to try out the rotary encoder and do something with the speaker.
Fifteen-minute warning?
Okay, thank you. One of the problems I ran into, and I don't know why it's not on every one of my rotary encoders, because they all came from the same place. But some of them, that's what happens when you pay 50 cents a piece or whatever I paid for a box of 14. Is there's a full step, so, and a half step when you're doing a rotary encoder, and I'll let you read up about it because it's not something I wanted to cover here. But if you're having to go 2 clicks to get anything to change, So I go click, click, and then the tone changes, and click, click, and the tone changes again. You have to go in and to the header file, to the rotary encoder, and get rid of that little hash marks right there. And what that does is in the header file, there's two different tables for what does the code coming out of the rotary encoder mean. And so now when it goes click, tone changes, click, tone changes, click, tone changes. And the other thing that happens is if you have it on half step and you try that, you don't get, and the rotary encoder doesn't need the half step, you get a different funny result that you have to then go back and put that in. So when you've got a problem, when you don't think your rotary encoder is doing what it's supposed to, go in the header file and see if that's an issue.
So is that just for hardware that can take advantage of the half step?
Well, I thought it was rotary encoders were meant to operate in half step, and some were meant to operate in full step. What it is how much resolution you want when you turn it. You know, if it's like 20 steps to go all the way around, if I'm doing half steps, I'll get 20. If I'm doing full steps, I might only get 10 changes as I go around. I don't know why the ones I've got, some of them work one way and some of them work the other one. At least physically on the outside, they look identical. I can't find a difference between the two parts. Okay, I threw this in just to let you know it's possible. Because your files, as you start writing more and more and more complicated files, what you've been doing so far is writing it all in one file, and it gets really long, and when you say, where did I handle that push button? Or where did I write to the display, and you start scrolling through hundreds of lines of code, you really get frustrated. So what you can do is you can break your program up into files, and it wasn't obvious to me how to do it, so I had to call my friend Carl Hines and say, how the heck do you do this? And what you do is you create files with names of .cpp. And then I write here, file. Oh, I thought I explained this somewhere, but let's get out of this. Come on. If you go, Carl, do you remember what you told me?
I can pull up the email. You do the show sketch folder, that should bring up the folder in which your sketch lives.
All right. Then
Now you have to save your sketch once. When you first bring it up, create it, you have to save it once, because otherwise it lives in temporary location, you will
Right.
never find that again. And now you can create files in here. On Windows, you can just right click and do a new text file.
Ah. Come on.
New text
New text document.
And this will create something called .text, and now you change the name to myfile.cpp or myfile.h. And then once you bring up the Arduino interface again, it will find these files and add them as empty files to the project.
Okay, thank you. And then you can put your code in there, so. I don't want to do that. I guess that's not very.
But creating these CPP files and header files, that is advanced Arduino programming.
Right,
Probably not something we'll get to today.
right. I just wanted to make the point, thank you, he's right, that I just wanted to make the point that when you start doing something, the files get really long, and you need some way to organize it. Oh, great. It's gonna make me go through everything, huh?
A good example for that is, and it is ham radio related, there is a tier project out there that runs on all sorts of different Arduinos by K3NG. And that is a pretty powerful application that allows you to do all sorts of fun stuff with a keyer, including learning modes where it just throws characters at you and you have to reply, and a few other things. And that is organized in separate CPP files for different types of functionality. So you go through that and you find a lot of header files and C++ files, and then configure it that way by going into these files and changing how defined options on or off to get certain configurations.
So that here, I put an article in, I broke it down, so like this tab here is the code practice oscillator, and then nothing more than close the key, it turns the buzzer on, and release the key, turns the buzzer off. So there's some code for that. And then you get to this is a decoder. Actually, you put a tone detector in front of the pin on the processor, so you get a 1 when the tone's on and a 0 when the tone's off. So I can hook the tone detector up to your radio. And so this will decode the Morse code that's coming in. This was the ambit keyer. This is a header file that has a bunch of constants in it that's beyond the scope of today. Random number, a random character generator for the code graphics oscillator. But you can see there's actually more of those on farther. The code just got too big, and I said, okay, I've got too many ideas, I've got to break it down into something I can work with. So now I can just work on one file, and I'm not affecting anything else. So that was the point of that.
So is it fair to say that this folder structure is sort of Arduino's alternative to a conventional makefile, right? If you were building a project in C, you put your files wherever you wanted to, and you'd have a makefile that says, here's where they are.
I'm
Include
going
them here,
to
right?
say it depends upon the compiler you're using. So if you've got a compiler from Etnal, I don't think you need a makefile.
I think we were just saying the logic is similar.
Right, okay, yeah.
Yeah,
It's just sort of, it's pre-written into it, here's where you're gonna look and no place else.
Yeah, thank you, Jeff, thank you. Any questions before we stop?
Have you used the web version of this tool?
No. They keep your files. You know, they're not on your computer. And if I want to sit in my son-in-law's house and not be bored, I'm going to take my computer with me, and I may not be able to get on his Wi-Fi. Who knows what reason? I just don't want to let them have it. That's all. Anybody else? On anything that we've done so far?
Carl Heinz mentioned conditional compilation. The compiler will do this. In other words, you can say, you can define a value and then use that to conditionally combine your debug statements.
Yes.
Yeah,
Okay.
there's no debug statements though.
Well, I mean the write lines.
Oh, okay.
You can say, okay, this is the debug version, and it goes right line, you know.
Oh, right, you could
But
put
then
in.
if you turn
I
that
see what you're
off,
saying.
then those are not compiled.
Yeah, you could make all the serial print statements conditional. Yeah. Has what we've covered so far been what you expected? Was it too much, too little? Okay.
I have a feeling there's a lot more.
Yeah, so I got a couple advanced topics. This was one of them, having the multiple files. The next one is just a little bit about the timer, so you know how complex it is and why they didn't write simple commands for the timer. The timer has a bunch of functions. The output compare, meaning the timer's running, and I put a number in this output compare register. When the timer is equal to that number, it does something to a pin on the output of the microprocessor. So I could say, here's where I use a delay that works. I could say, in 150 milliseconds, turn that pin high. And the timer will do it all by itself. You don't have to write. You wrote code to initialize the timer, but you don't have to go out and write code to put the pin high. The output compare will do that. Pulse width modulation, for controlling motors. You can write to the registers and say, here's what I want, and tell it to do pulse width modulation, and it'll send a series of pulses out one of the port pins, and then you can control the width of the pulse easily. You don't have to toggle the pin. The timer module in the processor is controlling the pin. Input capture is great if you're trying to measure how long is a DIT. You read the timer when the signal goes high. What you're really doing is the input capture register captures the value of the timer, because the timer's running at some fast rate versus how you're keying. And then you read the timer again when you release the key, and you subtract the two numbers, and now you've got the duration of that pulse when you're trying to decode Morse code. There's a timer counter, or you can just read the counter. For whatever reason you need to keep track of time, you can read the counter. It generates interrupts, and there are multiple clock sources. So there's the internal clock source, which is the 16 megahertz processor clock. And so you can divide that by 864, 256, or 1024. And then there's an external clock source, which means you have to have some kind of clock source to drive the pin on the processor with. So you might have a very stable 1 megahertz clock. It might be temperature compensated and tuned to WWV and all that. And so now you've got a 1 megahertz clock that's 1.000000 megahertz. And now you can have a very stable clock, no matter what the 16 megahertz clock is doing. If the 1 megahertz clock is stable, your timer for your 24-hour clock would be stable. And one last thing is this pin change interrupt. This is really cool. And there are interrupt pins on the processor, interrupt 1 and interrupt 2, and in the references you see attach interrupt and detach interrupt, and I think interrupt on and interrupt off, something like that. And they're talking about the 2 interrupt pins. And those 2 interrupt pins have a bunch of functions. When the signal goes low, you interrupt. It can interrupt on a falling edge, or it can interrupt on a rising edge. And we had one called logic level, and I didn't read to see what logic level was, but that's pretty cool. So if I only want to capture signal on the falling edge, I've got that interrupt pin. If I want to capture signal on the rising edge, I've got that interrupt pin. And so the falling edge occurs, it causes an interrupt. You write an interrupt routine that goes off and does something you wanted it to do based on that interrupt, based on that falling edge. But there's only 2 pins on the processors that have that. So if you've got 16 keys that you want to read, and they're going to be open, close, open, close, open, close, it's very hard to do with 2 pins. So they have this thing called pin change interrupt. It isn't as versatile because you can't control whether it's a rising edge or a falling edge or a low level. You get an interrupt on a falling edge, you get an interrupt on a rising edge. So you've got to constantly handle opening and closing of the switch. But I can assign it to, I think, all 22 I/O pins. So I have lots of capability if I want to read a keyboard. It does require a little bit of, manipulation of the data you're getting back, because you're going to read a port register. You're not going to use digital read and digital write. You're going to say port A is equal to, or keyboard is equal to port A. So when you read port A, you're going to get 8 bits, and now you have to figure out what do I do with 8 bits, not just 1 bit. On one hand, it's more complicated. On the other hand, I don't have to constantly look at pin 1, look at pin 2, look at pin 3, look at pin 4, look at pin 1, look at pin 2, over and over again. The pin change interrupt takes care of that, and I know when it closed, and I know when it opened. So I don't have to worry about it in between. Oh, it's closed. Is it still closed? Is it still closed? I did something because it closed, and when it opens, it'll tell me, and I can do something else.
Is that provided your keys are debounced?
This is the case where you will see every bounce if you don't debounce your keys. You know, every little jiggle of the line when you push that button or release that button will create an interrupt. So if you see, if you push the button and you get a close, open, close, you're gonna get 3 interrupts on the close of the key, and then when you release the key, you get it open, close, open, you're gonna get 3 more on the output. So you need to either handle it in the software, or you put a capacitor on it. And you keep increasing the size of the capacitor until it fixes it. Not always a good idea, but
12 o'clock.
thank you, because we are at, this is the end.
So, a question about the interrupts, so the edge triggering, so you could say raise the timer against the occurrence of the edge and measure frequency, like if you were building some kind of a decoder.
Right.
You could-
Well, that's, go back to the timer. You use the input capture. So you, on zero crossing, you would trigger the input capture to read a value from the timer, and so you save that value away. And then on the other zero crossing, you read, these are by interrupts. The input capture, you could do it, I guess you need an interrupt in there somewhere, but you get the point. I can read it here, I can read it here, I can read it here, so I know
The
the
period.
time for the half cycle, so I know the time for the periods, and I can calculate frequency. You're not gonna do 1 gigahertz. You might be able to do 1 megahertz.
You could do a packet modem.
Yeah. Audio would be easy. Okay, okay, so that we got to the 80, or most of the 85 slides. And so what I want to do is take a break. And then we can talk about actually writing a program. We can discuss which program we want to try to write and program while we're here. So I want to take a break for a little bit. Find the bathroom. I appreciate you sitting and listening intently. Us together was to try programming something. And so what I came prepared for was a simple 24-hour clock, or the rotor controller for this rotator, the digital interface for this rotor controller. No big deal. You got the display, and that's it. The rotor controller, you need 2 more LEDs, but you can use the serial print statement to tell you when you turn the relay on, turn the relay off, or turn the LED on, turn the LED off. So, because this would require a relay for each of these 3 switches, or for prototyping an LED, and then the meter is actually your pot on your board would be this pot here. So for these 3 switches, you could just use the serial print statement and say, you know, switch 1 close, switch 2 close, whatever. So any thoughts, clock or this digital interface to the rotor controller?
Yeah, I did top because we've got something to take home that we can use, if you like.
Okay, fair enough. Okay, you won't use this one anymore. We'll see if this works, so I can take notes.
Yay.
Come on, wake up. I don't want to see him. All right, why don't you like me today? Sound good? Oh, come on, right for me. Okay, technology isn't working. There we go. So, 24-hour clock. So that would be the output time. input would be the tick. What is it? A clock for one, a signal that creates the 1 second. And we're gonna ignore setting the time for the time being. That gets into reading switches and we wanna get done today.
We just turn the power on at midnight.
Well, almost. You hold the reset, you program in a start time, and you hold the reset button until 3 seconds before that start time, and you release the reset button, and it takes about 3 seconds for it to start running. So, yeah, you can work, you can do it, but then you gotta, if you need to reset it again, you have to wait till that time comes around. So what would be, I'm opening up to you, because I can tell you the answer, because I've got it all right here. And I don't want to give it to you. I want you to try so you can ask me questions as we go along. You want to just sit and try to write something, or you want to discuss how we're going to do it, like a flow chart? Okay, so we've got we'll call it a 1 second tick of the input. So this is the output. This is the input. So what's the process? How does a clock work? What happens?
We're counting ticks, converting them to seconds,
Okay,
and then we're calculating minutes and hours or whatever.
okay. So how would you create the 1 second tick? We've already seen most of the commands. That was one of the sheets I gave you. Oh, where is it?
Yes, so I would run the timer
There we go.
and read it and do modulo whatever 1 over
Okay.
1 second
Well,
was.
we're not doing the time. We're gonna, yes, but we're not going to do the timer because we've kind of really covered how to do that. We have to get out the data sheet.
Use the delay.
Yes. We would do it simpler. Because your clock, the delay works for now, because your clock isn't gonna do anything else during that 1 second. It's gonna increment time because of the 1 second tick, put it on the display and sit there. So we don't need to free the clock up to do something else just yet. So a delay is fine. How long would you make the delay? How fine do you want? I guess it's
1,000 milliseconds.
right. Okay. So you're gonna, have a delay 1,000. So after the end of that delay 1,000, what happens?
Increment out of a second term.
Okay, so how might you increment? Okay, let's go back. We got to define variables. So let's have some variables. What variables do you think we need?
ISEC.
What else?
Hours, minutes, and seconds.
Okay. Anything else we need?
AM, PM, maybe, or I don't know if you want to do it.
We're gonna do
24 hours.
We're gonna do 24 hour for now.
And you've got,
How about day, month, and year? You think that's all the variables we need to do a clock?
well, somewhere you've got to put in max, you've got to put a whole load of data. For instance, if you're doing day, month, year, you've got to put in the number of days in the month, and stuff like that.
We'll get there. Yes, you're right. Let's get the clock ticking first. Okay. Okay, so we've got all these variables, and so to get it started, you have to pick a day and a time, because we're not going to input anything with push buttons at this point. You might say, the seconds are going to be equal to 0. Let's always start seconds at 0. What time is it? We got to leave here at 2:30, so we'll say at 2:15. So the minutes might be 15, and the hours would be 14 for 2 o'clock. And today is, what day, the 21st? 22nd? 22nd, second month, and the year is 2020. Okay, so there's your variables, there's your initial condition for the clock. So the first step is, what are we gonna do when we get a tick?
You wanted this to be UTC, didn't you?
Well, we,
So your hour's 19.
okay. Well, at least I can turn a 4 into a 9. Thank you. I thought this up yesterday, using my iPad to put something up on the screen for you. I'm not that tech savvy.
I was just trying to figure out if it was still 22 or 23
Oh,
for the day.
it's still 22 for a couple
For a
more
little
hours.
while.
Okay, so we got to delay the first, I'll give you a hint, the first statement is delay 1,000, then what happens?
Sec equals sec plus 1.
Okay.
Modulo 60.
Getting too complicated, but yes, sec equals sec plus 1, or even easier, SEC plus plus. You don't have to add 1 to it, you just, it increments the second. It increments the second. Okay, you guys want to start writing something? Start putting in so we can test it. So, because the first problem is, how do I test that all these increments are happening properly? And we'll talk about that, but.
Well, reason it, these are integers, right?
Yes, everything can be integers. I can't remember if I used integers or characters. That's not it. Actually, I used everything's a byte but the year, which is an integer. Because year is 2020. Everything else is less than 256, so it doesn't have to be an integer. Okay, so I'll give you a hint. You've got to do a setup. You got to define something as a setup. How do I get out of this? Well, wrong thing. But you gotta set some initial conditions in your setup. And you have to decide whether you want to put something to the display immediately or send it out to the serial monitor immediately. And I recommend going to the serial monitor till we get a few steps into the process. I can't find my clock.
So yell if you need any assistance. I'm just gonna be shoulder surfing for a minute or two to see if anybody's stuck.
I could use a little.
Sure.
Okay. So, I'm assuming I needed to find minutes. Second.
Oh, good, you did. So go ahead, you got your startup and you got your. So, where do you want those to be located? Do you want those to be available to the loop? So you want to put them outside of setup and loop? You want to put them like up above setup? It's sort of convention is to put your goal stuff above.
Okay.
So if you hit, put your cursor there and hit something that turns them into, you can stick those up there. See, and then they become available, you don't have to, and, because otherwise you end up with a function that has a zillion parameters you pass in.
Okay.
And I've done that to myself when I get rid of them really fast.
Okay.
Did that make sense?
It does make sense, yeah. So,
Now, there's a couple different ways of going at this.
okay.
You know, you can keep each of the variables, or you can set an initial variable and just keep incrementing it, and then you use it to visually to get the other stuff. for the display.
Either way you want to go, you follow me?
No.
Or you could have just one variable, and the clock could just keep ticking, increment that time since we started the program.
Okay,
And then you can divide it, you get all the
okay,
you can, that way, it depends on whether you like keeping a bunch of variables, or you like keeping one thing and you need it, extract.
yeah, okay. All
So
right.
like, if it takes off 60 and then it's time to update the display, it takes off 60 ticks, 6,000 ticks, you know that's 6 seconds,
Okay,
right? So you're keeping on one variable.
okay,
Up to you, I'm just trying to say, whichever logical approach works best for you think.
right,
Okay.
okay, got it, okay,
So, what you want to do is set up, if you're going to keep them all, what you're going to do is set up your initial conditions for all. Right?
Yep.
And then you'll use your loop.
So,
okay.
now that we've increased.
Okay. So am I on the right path to do that, then am I on the right path here? You know,
Yeah, I would do that. I would like set those to 0 and then your startup.
You use that to set them to root values.
Okay.
You follow me?
Yep.
So they're initialized.
Okay,
Did we push the start?
yes it did, thank
So
you.
we say, if
And then the VFO on top, and I've been trying to figure out, well, I've got it working, but I got to try to go better so I can do slow scan TV transmissions better. And then later on, we'll have an image sensor rather than taking fixed images from the car. That's cool. That's it.
Oh, it's got all those sensors built right on it?
Air pressure, yep, they're all right on there.
It's so cool.
So Spring, happy birthday right now.
Really?
and then from there, this is when it runs, because it knows that.
Here's the best. So it has a sensor, a voice microphone sensor. So you gotta blow the candles out.
And then, once.
I haven't been in there, but when we come back, I'll look at that.
Oh, that is so cool.
And they may actually add.
I love it. Adafruit is a great resource, it really is.
I love, it's got the big tabs for the kids to use the alligator clips to.
I would do it.
Now, we used these guys a bunch for wearables that we were building with that.
Okay.